we move on to Vincent. Vincent Vanhoucke is from Waymo. So we go back to autonomous car.
Can you hear me okay?
Yeah, okay. So
right.
embodied AI, yes, sure.
I am indeed at Waymo, but with apologies to James and to everyone. I will not be talking about autonomous cars today. I will talk about the work that I've been doing at Google DeepMind prior to this. So this is a robot. This is a picture that is very, very similar to the picture that Manuela presented earlier. And a couple of years ago, we started to ask ourselves what this kind of nascent wave of Gen AI and large language models could do to that picture. So we started where things were the most obvious, the planning stage, turning really high-level plans into low-level plans. That was work called SEICAN. And one of the consequences of that was that suddenly we had an API to the different parts of the robots that was all based on natural language. So it was very tempting from there on to continue on that journey and to see what kind of other things we could replace with large multimodal models. So for example, if you replace the perception stack with a vision language model that actually has a dialogue with your planner using natural language, you get some very, very interesting results. And I'm not going to go into any of the results themselves. All the links are on the slides. Another thing that language models do very, very well is write code. In fact, it's one of the main uses of large language models today is to automate the process of writing code. And after all, a controller is a piece of code that can be expressed in various ways. So this was the idea behind things like code as policies, turning essentially the entire stack of your robot into a chatbot, the inner monologue on the robot that takes in as an input a narrative from the perception system, turns the high-level goal into a set of actions that you can do also in terms of natural language. And then a decoder that takes that natural language and turns it into actions that can be run on the robot. So that was nice, but language is just one modality, and it can sometimes also be a bottleneck. So we also looked into what happens when you try to merge those components more integrated and have a simple direct neural network that contains that performs both functions jointly and can pass gradients across and be optimized jointly. So the first work on this was Palmy. That was one of the first large multimodal models out there. And it was initially designed really with robotics as an application in mind, not just the general sort of visual Q&A and sort of visual and understanding that those large multimodal models are being used most for today. So that was encouraging. Why stop there? We also started looking into what it means to turn this kind of vision to action into a large-scale transformer model in a similar fashion. So that was called RT1 initially. Again, end-to-end transformer-based pixel-to-action model. And then from there, the logical conclusion was to just fuse everything, right? So this was work called RT2 initially. We had a successor work called RTX that expanded that to multiple robots in parallel. That was ICRA's Best Paper Award last year, or this year. And then we also had a number of works that built upon that foundation. Once you have something that looks like this, there's a lot of very natural, very nice properties that start to emerge from this kind of end-to-end architecture that incorporates a lot of the information coming from the web through language and a lot of the information that's also coming from images on the web. You get some degree of transfer between them, which is really interesting because that means it kind of breaks the curse of data in robotics. It's always really hard to collect lots of robotics data, and a lot of that data tends to be collected for no other reason than providing visual diversity or semantic diversity. So if your robot doesn't need to learn explicitly about who Taylor Swift is to be able to identify Taylor Swift and act on a picture of Taylor Swift. Your robot doesn't need to learn how to do math or to recognize what a drawn digit looks like. It can leverage all the data from the web to perform those kinds of tasks. So that's a really nice property, this kind of transfer, that's kind of really helps break the need for collecting a lot of robotics data. One of the nice things when you have a robot that is also driven by natural language goals is that you can actually give it some much higher level goals. So this is an example of an experiment we ran where we just told our robots that their goal was to just go out and play, go and find interesting things to do. The goal for us was to try and collect data automatically and collect more diverse data. So we basically let our robots loose in our kitchen and gave them lots of toys to play with. And they started playing. That got really, really interesting from my perspective because we had to solve a number of questions around safety, around what was okay to task a robot to do completely autonomously without human supervision. They're a big fan of all those towels, those napkins. And it started to sort of feel materially different in terms of what we were doing with autonomous robots by just prompting them with high-level commands. So I want to just go back to this a little bit, because here we are. We have a robot that is now can be tasked using a natural language goal. And language is really good at operating at basically all levels of abstractions. Right? You can tell the robot, move right 2 millimeters. That's extremely low level. But you can also go, pick up the cup, or make me a coffee, or go explore and play, right? All of those abstractions can be expressed very naturally using natural language. And if your large language model is able to turn that into an actionable plan, then you can interact with your robot at any level of abstraction that is demanded by the task. But you can also take it a little bit further. You can also make the goal be a life goal, right? You can make the goal be a value system that your robot is expressing, like be safe, be a good robot, act as a service robot. That's a goal. That's something that can be expressed in natural language. And if your large language model is capable of turning that into something actionable that influences the robot's action, then you can basically provide a blueprint for how a robot is meant to behave. The reason that got me excited is one of my colleagues pointed out that in our code base of those robots that were playing around in the kitchen, we had this little snippet there. You might recognize it. This was a snippet of text that was basically provided as part of the prompt for the robot. And think about it. Think about the robot you have in your lab, right? Imagine somebody comes to you and says, hey, I want your robot to implement Asimov's 3 laws of robotics. Go do it. I think most people would be like, I have no idea where to start. Like, I wouldn't, that doesn't really jive. The laws of robotics are a literary device of sorts, and connecting that to actual actions feels out of reach. But suddenly we have this little bit of connection of, hey, here is a piece of narrative about a value system that is actually being plumbed all the way through the robot down to actual actions. We have a connection between a constitution for the robot and the actions that the robots take. This is actually not benign. We've seen in other contexts, there was a lot of work, for example, from Anthropic on the subject, the concept of constitutional AI, where you have a prompt that provides a constitution for the AI and causes the AI to behave in a way that is consistent with the prompting. So I'm calling this constitutional embodied AI, and I think it's a very interesting area that we should be looking into and studying, because now we actually have the means of studying it, because through this link we have a quantifiable way of measuring and evaluating its effectiveness. So imagine being able to study semantic safety, value alignment, preferences, difference in depth, right? This does not substitute itself to all the safety layers you have on your robot. It can be just one other layer that induces the robot to do things according to a set of values. So this is my pitch today. I mostly wanted to ask the question to the community, should we be studying this? Is this something that could enable the practical study of value alignment for robotics and embodied AI at large? That's it. Thank you.
Vincent. We have time for one quick question for Vincent. Maybe there.
A really impressive talk.
Okay.
My question, I think, for a lot of us in the room, when we think about the LLMs, two big things come to mind. One is the dirty word computation, which I know we don't like to talk about, but computational cost. And then the other question, I think here, still we have the question about edge cases and failure modes. So I was curious if you could maybe speak to those two things very briefly.
Yeah, none of the things I was discussing here really addresses the question of edge cases, right? And if you try to really scale things into the real world, which is what I'm starting to look at a lot more now that I'm Waymo, the edge cases kind of define the space of problems and the design space that you use for your robots. So they're essential to even designing the solution that you're approaching. I don't think we have good solutions today to mesh this kind of AI-first approach and a design space that requires you to never fail in any scenario and to have a very high degrees of safety. That's where the really interesting research is, in my opinion. I think there's really a lot of things we could do there to keep the power of AI alive, right? Not completely shut it down, but also make it compatible with actual deployment in mission-critical scenarios in the real world.
Thank you again, Vincent.